right now, 15.4 billion miles from wherever you happen to be sitting, a spacecraft with less computing power than a birthday card is beaming data home through a backup transmitter that last powered on in 1981. It is the most distant human-made object ever built. And the boundary it was dispatched to cross, the outer edge of our solar system, turned out to be nothing like anyone had predicted. We are going to trace what Voyager actually encountered out there, from a hidden love story etched in brainwaves to a wall of pressure sitting in interstellar space that science cannot explain. If this story grabs you the way it deserves to, hit subscribe now, because what follows will permanently alter how you think about our position in the galaxy. Let's get into it. On August 25, 2012, NASA convened a press conference that landed on every major front page on Earth. Voyager 1, a spacecraft no larger than a compact car, had officially become the first human-built object to pass into interstellar space. 40 years of flight, more than 11 billion miles from home. A frontier crossed that no machine, no satellite, no probe had ever approached. The announcement arrived with the gravity of a civilization-defining instant, and for several days the world received it exactly that way. Then the argument erupted. Within weeks of that press conference, a quieter counter-narrative began spreading through the heliophysics community. Several leading researchers rejected the claim. The data, they insisted, was ambiguous. One crucial measurement had refused to fit the theoretical predictions. Some maintained the spacecraft was still inside the heliosphere, the protective bubble driven outward by charged particles streaming off our star. Others believed Voyager had slipped into a region nobody had ever defined, something suspended between inside and outside. The dispute dragged on for over a year before NASA issued formal confirmation in September 2013. Even that did not quiet the dissenters. Leonard Fisk, a well-regarded heliophysicist who had spent decades mapping our star's magnetic reach, maintained as late as 2022 that the probe had never genuinely departed the heliosphere. His position was precise, rooted in magnetic field data that we will return to shortly. He was not alone. A notable fraction of the scientific community regarded the announcement as premature. Some published papers contending the craft had entered a strange region that merely resembled interstellar conditions. Others doubted whether instruments engineered in the early 1970s could reliably distinguish a genuine crossing from a local fluctuation. So sit with this. The single greatest milestone in the history of robotic spaceflight is disputed by the very researchers whose careers made it possible. The public was told the craft had exited the solar system. Scientists were fighting over what exiting even means. And buried at the center of that argument is a question that nearly half a century after launch remains genuinely without resolution. Where does the solar system actually end? That question sounds straightforward. It has the kind of clean, bordered shape that implies a clean, bordered answer. A line you can identify, a mark on a chart. Except every piece of data this spacecraft has returned across 48 years has made the answer more difficult, more peculiar, and more unresolved than it was before any data existed at all. The definition keeps migrating. The boundary keeps retreating. The evidence keeps undermining itself. We are going to follow that evidence from a summer intern's hand-plotted graph in 1965 to a corrupted memory chip 15 billion miles from Earth. From a $900 million mission that Congress eliminated to a backup transmitter that revived after 43 years of silence. What Voyager found at the outer edge of our solar system demolished models, ended careers, vindicated outcasts, and deposited science with more unanswered questions than it held when the journey began. The investigation starts with a graduate student, a pencil, and a once-in-multiple-lifetimes alignment of 4 outer planets that nobody had registered. In the summer of 1965, a young graduate student named Gary Flandreau stepped into a corner office at the Jet Propulsion Laboratory in Pasadena, California. He had been handed a relatively routine assignment as a summer intern. Calculate future flight paths for missions to the outer planets. Nobody anticipated what he would uncover. What he did next would make the most ambitious space mission in history achievable. And it began with nothing more advanced than a pencil and a shelf of orbital reference tables. Flandreau settled in with charts, planetary data, and those reference tables. No computer simulations, no orbital modeling software. Such capabilities barely existed in 1965. He mapped the positions of Jupiter, Saturn, Uranus, and Neptune across the coming decades, tracing arcs by hand across sheets of graph paper. And, concealed within those arcs, he spotted something extraordinary. All 4 gas giants were converging on the same side of our star, in an arrangement that would allow a single spacecraft to catapult from one planet to the next, using each world's gravity as a cost-free accelerator. The window for this rare configuration would open in the late 1970s. It would not recur for 176 years. Think carefully about that interval. The last time these 4 planets fell into this arrangement, the American Revolution had not yet started. Mozart was still a boy. The next time this window opens, the year will be approximately 2153. Every person alive in 1965 had exactly one opportunity to exploit this trajectory, and that opportunity carried an expiration date measured in just a few short years. Flandreau's discovery ignited a surge of energy inside the Jet Propulsion Laboratory. Engineers started sketching spacecraft configurations. Physicists calculated the mechanics of gravity assists, working out how much fuel could be conserved by deflecting from planet to planet rather than traveling direct. Each planetary flyby would curve the spacecraft's path and add velocity. A cosmic slingshot that transformed an impossible voyage into a realistic one. The concept was breathtaking. A single mission could reach all 4 outer planets in barely more than a decade, covering distances that conventional propulsion would require a lifetime to traverse. 2 spacecraft ultimately lifted off from Cape Canaveral, separated by 16 days. The second to depart, on September 5, 1977, was labeled Voyager 1 and placed on a faster trajectory designed to reach Jupiter and Saturn ahead of its twin. Voyager 2 had actually launched first on August 20th, but its more gradual path meant it would arrive later at every destination. The naming was an administrative oddity that continues to confuse people decades on. Together, these twin probes carried instrument suites built for planetary flybys. Cameras for imaging, cloud systems and moons, magnetometers, cosmic ray detectors, and a power supply that would become the most defining constraint on the entire mission. They also carried something else entirely, a golden record mounted on each craft's exterior, loaded with sounds and images assembled to represent life on Earth. We will return to that record and the remarkable human story woven through it. For now, what matters is the trajectory itself. Gary Flandreau had located the window. 2 spacecraft flew through it, and a mission that would ultimately push further from Earth than anything humans had ever constructed, began with a hand-traced diagram and a 176-year cosmic coincidence that a summer intern spotted when no one else had looked. The problem was that Congress had tried to kill the entire undertaking before a single rocket cleared the launch tower. The mission that Flandreau's discovery made possible was originally known as the Grand Tour. It was precisely as bold as that name implies. NASA envisioned dispatching multiple probes past all 4 outer planets, gathering measurements at each stop, assembling a thorough portrait of the solar system's most remote worlds. The projected cost was $900 million. In the early 1970s, that figure landed on congressional budget desks like a detonation. Congress eliminated the Grand Tour. The political logic was uncomplicated. $900 million was a staggering sum for an uncrewed mission, at a moment when the Apollo program had already exhausted public enthusiasm for expensive exploration. The Vietnam War was consuming the federal budget. Legislators saw no pressing urgency in visiting gas giants. The planetary alignment Flandreau had identified was a fascinating curiosity, but it carried no national prestige equivalent to what had powered the race to the moon. The outer planets would still be there, or so the argument ran, deliberately overlooking the fact that the alignment window absolutely would not be. So the engineers at the Jet Propulsion Laboratory did what engineers always do when the funding evaporates. They repackaged the proposal. The Grand Tour became Mariner Jupiter-Saturn, a stripped-back version carrying a budget of roughly $250 million, less than a third of the original figure. The formal mission scope was restricted to Jupiter and Saturn only. Uranus and Neptune were cut from the authorized itinerary entirely. Here is the pivotal detail that reframes this entire investigation. The extensions to Uranus and Neptune were never built into the approved plan. They were folded in afterward, one at a time, approved incrementally, only after each earlier flyby delivered results impressive enough to justify additional funding. Every single discovery Voyager made beyond Saturn happened on borrowed time with borrowed money. Aboard spacecraft that were officially supposed to have concluded their mission billions of miles earlier. The termination shock, the heliopause crossing, the stagnation region, the anomalous cosmic rays, the magnetic field puzzle, pressure front 2. All of it. Every revelation that inverted our understanding of the solar system's edge came from a mission that, on the books, should have ended at Saturn's orbit. This is a matter of record. The budget authorizations are traceable through NASA's own documentation. The Uranus flyby was authorized only after Saturn produced spectacular results. Neptune followed. Approved only after Uranus surpassed expectations. Every extension was a wager. Any Congress, any budget committee, any single appropriations vote could have terminated the mission at the edge of the authorized itinerary. The scientists and engineers who campaigned for each extension understood they were requesting something that could be refused at any moment. Which raises a question worth dwelling on. If the Grand Tour had survived, if the complete $900 million had been committed, would Voyager have been designed to different specifications? Would alternative instruments have been included? Would the power systems have been engineered to endure longer? The spacecraft operating now, pushing through interstellar space on under 300 watts, were built for a Jupiter and Saturn mission. Everything beyond that is improvised. Every instrument still running was intended to shut down decades ago. Science assumed the Grand Tour was the trajectory. What unfolded instead was something messier, more financially precarious, more politically fragile, and ultimately more consequential than any purpose-built flagship mission could have achieved. A spacecraft designed for the near edge of the outer solar system ended up at the outer edge of everything. But arriving there required a decision at Saturn that would shadow the mission for decades afterward. In 1980, Voyager 1 reached the ringed planet, and NASA faced a fork in the road with no path back. Saturn's largest moon, Titan, was a high-priority scientific target. It harbored a dense, nitrogen-rich atmosphere, the only moon in the entire solar system known to possess one. The possibility of studying that atmosphere at close range was extraordinary. Getting near enough to do so with precision demanded a specific flight path computed to fractions of a degree. And that path carried an irreversible consequence. The gravity assist required to swing close to Titan would throw the spacecraft upward out of the plane in which all the planets travel. Once locked onto that course, there was no returning. Pluto, which certain mission planners had hoped to visit, became permanently out of reach. Every remaining planet became permanently out of reach. The Titan flyby would convert Voyager 1 from a planetary explorer into something fundamentally different. A projectile aimed at the outer edge of the solar system with no planned stops remaining between Saturn and whatever waited beyond the heliosphere. NASA chose Titan. From that moment, the spacecraft's fate was fixed. It would travel outward, alone for as long as its instruments and power supply could endure. The only things it would encounter were the boundaries of our star's reach, whatever lay beyond them, and the vast empty distances separating everything. The entire future of the mission became a question of endurance rather than destination. Before launch, though, the team had prepared something for the long silence ahead. Carl Sagan, the astronomer who had already become the public face of planetary science, led a project to create a message from Earth that would ride aboard both spacecraft. The result was the Golden Record, a gold-plated copper disc carrying 116 images, greetings in 55 languages, 90 minutes of music gathered from cultures around the world, and an assortment of natural sounds ranging from wind and ocean surf to bird calls and laughter. The record cost $18,000 to produce. The Beatles had agreed to allow Here Comes the Sun for inclusion, one of the most recognizable songs ever recorded. Then, the record label controlling the rights demanded $100,000 in licensing fees. The entire record's budget was less than a fifth of that demand. The song was cut. In its place, the team secured other pieces of music that could be licensed for free or at minimal expense. What did actually make it onto the disc is, in certain respects, stranger and more deeply human than any popular song could have been. Anne Druyan, a creative director collaborating with Sagan on the record project, had her brainwaves captured by an electroencephalograph and compressed into approximately 1 minute of audio for the disc. She and Sagan had fallen in love during a late-night phone conversation about the project just days before the recording session. They had told nobody. As the electrodes traced her neural patterns, Druyan later recalled thinking about the full sweep of human history, about the nature of love, and about what it felt like to be falling for a specific person in a specific moment. Those brainwaves are now aboard both Voyager spacecraft, over 15 billion miles from the laboratory where they were captured. Carl Sagan later separated from his wife, who had also contributed to the Voyager project. It was tangled, painful, and entirely human. The Golden Record carries the imprint of that complicated episode along with everything else. With Titan examined and Pluto sacrificed, the craft turned its instruments outward. Ahead lay the space between planets, then the space between stars. The question shifted from what the probe would fly past to what invisible frontier it might eventually cross. Scientists held a clear picture of what that frontier should look like. It had been codified in textbooks for decades, and virtually all researchers agreed on the details. For more than 55 years, the model of our star's influence on surrounding space was clean, intuitive, and nearly universally embraced. Our star continuously drives a stream of charged particles in every direction. A torrent of protons and electrons racing outward at hundreds of miles per second. Physicists call this the solar wind. That wind inflates an enormous bubble hundreds of times wider than the distance from our star to Earth, pressing outward against the thin gas and dust that fills the space between stars. This bubble has a name, the heliosphere. At some remove from our star, the solar wind decelerates. It slows from supersonic velocities to subsonic speeds at a boundary called the termination shock. Picture a bullet dropping below the speed of sound. The physics are comparable. Beyond the termination shock, the wind continues outward but more sluggishly, compressed and heated as it pushes against the interstellar medium. This zone between the termination shock and the bubble's outer wall is called the heliosheath, and at the heliosheath's far edge sits the heliopause, the wall, the final boundary where our star's dominion yields to the galactic environment. Cross the heliopause, and by the most widely accepted definition, you are outside the solar system and inside interstellar space. Every textbook depicted this bubble with a characteristic silhouette. Because our star moves through the galaxy at a considerable clip, the heliosphere was illustrated with a blunt nose pointed in the direction of travel, and a long tapering tail streaming behind like a comet. The analogy was tidy. The physics appeared straightforward, and nobody had observations to challenge it. For over half a century, the comet-tail heliosphere became one of those embedded assumptions that an entire discipline constructed upon without ever interrogating. It appeared in textbooks, on diagrams, in grant applications, and in the mental models of every heliophysicist on the planet. Stamatios Krimaigas, a researcher who would later play a significant role in interpreting Voyager data, described it directly. You do not accept that kind of change easily. The whole scientific community had assumed for over 55 years the heliosphere had a comet tail. The model also predicted specific, measurable events at each boundary. At the termination shock, the solar wind would decelerate sharply. A population of particles called anomalous cosmic rays would be accelerated to their observed velocities right at the shock front, bouncing back and forth across the boundary like a ball picking up speed between two approaching walls. At the heliopause, the magnetic field would pivot sharply, swinging from our star's field orientation to the galactic field orientation. This rotation was regarded as the single clearest indicator that a spacecraft had transitioned from inside to outside. Scientists anticipated Voyager would confirm each prediction in turn. Termination shock. Solar wind decelerates. Confirmed. Heliopause. Magnetic field rotates. Confirmed. Interstellar space. Galactic cosmic rays dominate. Confirmed. A standard checklist of boundary crossings validated in sequence. The models had been developed by brilliant minds working from rigorous physics. Decades of theoretical refinement had sharpened the predictions. The heliosphere was supposed to be a settled problem. with Voyager serving as the final proof rather than the opening chapter of a fresh mystery. On February 14, 1990, the spacecraft paused its outward journey long enough to swivel its camera backward, and what it caught in that single frame would reshape the emotional weight of every boundary crossing still ahead. The image reached Earth as raw data transmitted at 160 bits per second from roughly 3.7 billion miles away. When assembled, it showed our planet as a pale speck of light occupying 0.12 pixels within the camera's field. Scattered light diffracted through the camera's optics crossed the image in bright bands, and Earth sat within one of those bands, barely distinguishable from a flaw in the lens. Carl Sagan would later use this photograph to produce one of the most quoted passages in the history of science, writing, "Every conflict, every love story, every civilization that had ever existed, reduced to a fraction of a single pixel viewed from 40 astronomical units." But the scientific consequences were distinct from the poetic ones. At 40 astronomical units, Voyager 1 had covered less than half the distance to the termination shock. The heliosphere's inner boundary remained decades of travel time away. The edge of the solar system was still a theoretical construct, a line on a projection somewhere in the future. After capturing the pale blue dot, mission controllers made a pragmatic decision. The cameras were shut down permanently. Voyager 1 would never image anything again. The power those cameras consumed was needed elsewhere for the instruments that would matter when the spacecraft eventually reached boundaries that cameras could never have recorded in any case. You cannot photograph the termination shock. You cannot capture the heliopause on film. These boundaries are invisible, defined by particle counts and magnetic field readings, not by light. What followed was 14 years of near silence. The spacecraft continued outward at roughly 38,000 miles per hour. Its instruments ran continuously, sampling the solar wind, tallying cosmic rays, mapping magnetic field direction and magnitude. The data drifted homeward at 160 bits per second, through a signal so faint that its power arriving at the enormous receiving antennas of the Deep Space Network registered at 10 to the power of -16 watts. To put that in perspective, a standard household light bulb draws 60 watts. The signal from the most distant human-built object ever constructed delivers a fraction of a watt so infinitesimal that you need 16 zeros after the decimal point to write it down. The craft's onboard computer held 3 million times less memory than a modern smartphone. Its entire data architecture was conceived in the early 1970s, before the first Apple computer was imagined, before the Internet, before anyone had envisioned a handheld device. Every measurement, every cosmic ray count, every magnetic field reading was captured, formatted, and transmitted by hardware that predated the personal computer era by nearly a full decade. For 14 years, the instruments showed a gradually weakening solar wind and a slowly rising cosmic ray count. The trends aligned with the models. The approach to the termination shock looked exactly as expected, a methodical, orderly progression toward the first boundary. The scientific community anticipated a clean, validating arrival. December of 2004 shattered that expectation. The data arriving in those transmissions carried signatures that matched nothing on any whiteboard at any institution on Earth. The first boundary had been reached, and the shock when researchers analyzed it was not the confirmation the field had spent decades waiting for. It was the beginning of every assumption coming undone. On December 16, 2004, Voyager 1's instruments registered a sharp transition. The solar wind speed dropped. Particle energies shifted. The signatures pointed to a single interpretation. The spacecraft had crossed the termination shock at 94 astronomical units from our star. After 27 years of travel and decades of theoretical work, the probe had reached the first boundary of the heliosphere's outer edge. The scientific community held its breath. Then came the wait for the second data point. Voyager 2, traveling a different trajectory on the opposite side of the heliosphere, was still en route. It crossed the termination shock on August 30th, 2007, 3 years behind its twin. The distance from our star at that crossing was 84 astronomical units. 84 compared to 94, a gap of 10 astronomical units. In miles, that difference is approximately 930 million, greater than the distance from our star to Saturn. Let that register fully. The two spacecraft had crossed the same physical boundary at distances separated by roughly a billion miles. The heliosphere, which every model had assumed was broadly symmetric, was profoundly uneven. Something external was applying more force on one side than the other. The interstellar medium, the thin gas and magnetic field filling the space between stars, appeared to be denser or more forceful on the flank where Voyager 2 traveled. The bubble shielding our solar system was being compressed, deformed, pushed inward on one flank while extending further outward on the other. A single measurement can be dismissed as an anomaly. Instrument noise, a transient disturbance, a local fluctuation that happened to coincide with the crossing. Two measurements from separate spacecraft traveling different paths, years apart, pointing to the same conclusion, constitute evidence demanding explanation. The symmetric heliosphere, a cornerstone of 5 decades of theoretical modeling, was finished as a defensible assumption. The confirmation scientists had anticipated instead delivered a contradiction. The boundary was real. Its location was deeply non-uniform. The shield surrounding our solar system was warped, distorted, shaped by forces the models had completely failed to capture. That alone would have been enough to rewrite the textbooks. But the termination shock carried a second revelation. And this one struck at the foundation of particle physics models that had been treated as settled for years. The anomalous cosmic rays were supposed to gain their energy at this boundary. The termination shock was, according to prevailing theory, the particle accelerator. Material from the interstellar medium that had been ionized and swept into the solar wind would rebound back and forth across the shock front, gaining velocity with each pass until it reached the extreme speeds observed by instruments closer to our star. The mechanism was theoretically clean and even elegant. The termination shock was the engine powering one of the most energetic particle populations in the entire heliosphere. Voyager 1 crossed that engine. The anomalous cosmic ray count did not peak. It did not flatten. It kept climbing. Beyond the shock, deeper into the Helios heath, the particles continued accumulating energy from an unidentified source. The boundary that was supposed to supply the explanation turned out to demand one of its own. Whatever was energizing those particles was either further out or was operating through physics that no existing framework had described. The question of where the solar system ends had just grown substantially more complicated. Because if the first boundary was already this far wrong, what would the second one expose? When Voyager 2's instruments recorded their version of the termination shock crossing, the data included something that made researchers at the Applied Physics Laboratory go visibly still. Pickup ions, atoms from the interstellar medium that had been stripped of their electrons and absorbed by the solar wind were carrying vastly more energy than any model had foreseen. The theoretical frameworks had acknowledged these particles, but had drastically underestimated their contribution to the overall energy budget. Ralph McNutt, reviewing the data from the Voyager 2 crossing, offered a response that would become well known within the heliophysics community. Confronted with the numbers from the termination shock instruments, his reply was a single word: wow. The pickup ions were significant because they represented a particle population that the models had essentially treated as inconsequential. Background noise. Passengers on the solar wind, present but dynamically irrelevant. Instead, they were carrying a substantial portion of the total energy budget at the termination shock. The minor players were in reality heavyweights that had been invisible to theory for decades, dominating the energy dynamics of the very boundary where they were supposed to be negligible. Combined with the anomalous cosmic ray puzzle from Voyager 1's earlier crossing, the emerging portrait of the termination shock was fundamentally unlike the one in the textbooks. The boundary existed. Its essential character, a transition from supersonic to subsonic solar wind, was confirmed. But nearly everything else about it, its distance from our star, its symmetry across the heliosphere, its function as a particle accelerator, and the energy balance of the particles within it, deviated from predictions in ways requiring either new physics or completely rebuilt models. The investigation was approaching its most significant boundary: the heliopause, the outer wall of the heliosphere, the line dividing our star's domain from interstellar space. Every prediction that had failed at the termination shock elevated the stakes for what would happen at the next crossing. If the models were this wrong about the first boundary, the boundary considered simpler and better understood, could they be trusted about the second? There was another complication, a practical one unrelated to theoretical physics. An engineering failure from decades earlier was about to collide with the most important scientific measurement of the entire mission. To detect the heliopause and actually confirm that a spacecraft had crossed from inside the heliosphere to outside, researchers required one category of measurement above all others: the density, temperature, and behavior of the plasma enveloping the spacecraft. Was the probe submerged in the hot, thin plasma of the solar wind, or had it entered the cooler, denser plasma of the interstellar medium? The instrument designed to supply that answer was the plasma science experiment. It measured charged particles directly, offering the clearest possible view into the spacecraft's surrounding environment. Voyager 1's plasma science experiment had gone dark at Saturn in 1980. The single instrument most essential to confirming the crossing had been non-functional for over 3 decades by the time the spacecraft approached the heliopause. The detector that would have provided unambiguous direct measurements of the plasma transition had failed at the worst conceivable moment in the worst conceivable location. It had been dead for longer than many of the scientists now interpreting the data had been alive. Voyager 2 still carried a functioning plasma detector. But Voyager 2 was years behind, still working through the heliosheath. The spacecraft nearest the edge, the one that would arrive first and make history first, was effectively operating without the single measurement that mattered most. Scientists would need to find another route to confirm whether the craft had crossed the boundary. They would have to improvise a heliopause detection without a plasma detector. The team pivoted to indirect approaches. The plasma wave instrument, originally designed to study oscillations in magnetized plasma near the giant planets, could estimate the density of the surrounding medium by measuring the frequency of naturally generated plasma waves. Higher frequencies indicated denser plasma. The cosmic ray instruments could monitor shifts in particle populations. The magnetometer could track changes in field intensity and direction. Together, these instruments could assemble a circumstantial case for or against a crossing. But circumstantial evidence invites disagreement, and disagreement was precisely what materialized. Between 113 and 122 astronomical units from our star, something was waiting that would make the improvised effort far more difficult. Between 113 and 122 astronomical units from our star, Voyager 1 entered a region that had no name because nobody knew it existed. The stagnation region, as researchers would eventually label it, had never appeared in any model. No theoretical framework had predicted its presence, its position, or its behavior. The solar wind, that constant outward stream of charged particles, had been slowing for years as the probe penetrated deeper into the Helios Heath. The gradual deceleration was expected. What occurred at 113 astronomical units was something else entirely. The radial velocity of the solar wind fell to 0. The flow that had been blowing outward from our star across billions of miles simply stopped moving. Then something stranger occurred. The wind went beyond stopping. It reversed direction. Instruments recorded lateral and backward flows as if the solar wind were folding back on itself, tumbling in directions bearing no relationship to the expected outward pattern. The heliosphere appeared to be collapsing inward in this region, the wind stacking up against some external resistance and rebounding in disordered, directionless motion. For 9 astronomical units, approximately 840 million miles, Voyager 1 traversed this chaotic zone. The solar wind was present but aimless, its energy dissolving into turbulent eddies rather than sustaining any coherent direction. The magnetic field fluctuated, erratically. Particle counts oscillated without pattern. Everything about this region pointed to a system under extreme pressure. A bubble being squeezed from the outside with sufficient force to arrest and reverse a wind that had been blowing steadily outward across billions of miles in every other region the spacecraft had traversed. The stagnation region was a clue, a vast, conspicuous, 900 million mile wide clue that something complex was occurring at the boundary. The heliopause, wherever it was clearly not going to present itself as a clean demarcation. If the approach was this disordered, the actual crossing would carry complications no model had prepared researchers to expect. Consider what the investigation had established at this point. The termination shock was 10 astronomical units closer on one side of the heliosphere than the other. Anomalous cosmic rays were not being accelerated where decades of theory said they should be. Pickup ions were carrying energy that existing models had disregarded entirely. The one instrument required to confirm the heliopause crossing was dead, and now a region of reversed chaotic solar wind occupied the space immediately before the boundary. A buffer zone 900 million miles wide, whose existence was a complete surprise to everyone. Every model had forecast a sequence of clean transitions, wind slows, wind stops, cross the boundary, enter interstellar space. Instead, the approach resembled a system collapsing in stages, with each stage more disorganized than the previous. The textbook diagrams with their tidy concentric zones and crisp boundary lines bore almost no resemblance to what the instruments were actually measuring. And somewhere ahead, past the stagnation region, past the turbulence and the reversed flows and the fractured magnetic fields, the heliopause boundary where the solar wind terminates and the interstellar medium begins. The moment the entire mission had been building toward for 35 years. Voyager 1 was approaching it carrying a dead plasma detector, a demolished set of model predictions, a stagnation region behind it that should never have been there, and a team of scientists who would have to argue about what the data signified because they could no longer measure the one thing that would have settled the matter directly. The crossing, when it came, would produce the largest surprise yet, and it would ignite a controversy that lasted more than a year. On August 25, 2012, at 121.6 astronomical units from our star, Voyager 1's instruments recorded a dramatic transition. Galactic cosmic rays, high-energy particles originating from supernova remnants, neutron stars, and other violent events distributed throughout the Milky Way, surged upward sharply. The count jumped by a factor of 3. Simultaneously, the lower energy particles tied to our star's influence plummeted. The two measurements moved in opposite directions with a decisiveness that left minimal room for alternative interpretation. By every particle-based measure, the spacecraft had crossed the heliopause. But one critical measurement refused to cooperate: the magnetic field. Every model of the heliopause had predicted that, at the boundary, the direction of the magnetic field would pivot sharply. Inside the heliosphere, the field is shaped and oriented by our star. Outside, the galactic magnetic field dominates and points in a different direction. The transition from one field to the other was supposed to generate a measurable, unmistakable rotation in the magnetometer readings. This was the defining signature, the single most anticipated confirmation that a spacecraft had vacated our star's domain and entered interstellar space. The rotation never materialized. The field intensity changed, that much was certain, but its direction remained essentially unchanged on both sides of the boundary. The compass needle, in a manner of speaking, should have swung. It held steady. The implication was staggering. Either the models were wrong about the magnetic field at the heliopause, or the spacecraft had not genuinely crossed the heliopause, or the boundary itself was something fundamentally unlike what anyone had conceptualized. This missing signature threw the entire crossing into question. Inside the heliophysics community, disagreements ignited immediately. Researchers who had spent entire careers constructing models of the heliopause confronted data that undermined the single prediction they had considered most reliable. Some accepted the particle-based evidence and treated the magnetic anomaly as a puzzle to be solved separately. Others insisted that without the magnetic field rotation, the crossing could not be considered verified. The argument persisted for more than a year. Papers were submitted staking out both positions. Conference sessions deteriorated into tense exchanges. The public had been told the probe had left the solar system. Behind closed doors, the scientists responsible for that announcement were fighting about whether it was factual. And here is the detail that gives this failure its deepest significance. When Voyager 2 crossed the heliopause 6 years later at a different distance, on a different trajectory, on the opposite side of the heliosphere, the magnetic field direction again failed to change. The identical anomaly, the same absent rotation. Two separate crossings separated by 6 years and billions of miles, producing the same inexplicable result. This was confirmed. Replicated data from two independent spacecraft. The magnetic field at the heliopause behaves in a way that no model in the history of heliophysics had anticipated. The question of whether Voyager 1 had truly departed was about to acquire its most prominent skeptic, and his position would hold up for nearly a decade. Leonard Fisk was not a provocateur or a peripheral figure. He was one of the most distinguished heliophysicists in the field, carrying decades of published work on our star's magnetic influence and the dynamics of the solar wind. When he examined the Voyager 1 data from August 2012, he arrived at a conclusion that set him against NASA's public announcement. The spacecraft, he argued, had not exited the heliosphere. His reasoning centered on the magnetic field. If Voyager 1 had genuinely entered interstellar space, the surrounding magnetic field should reflect the galactic environment. The direction should have shifted. It had not. Fisk offered an alternative interpretation. The probe had entered a previously unknown region still within the heliosphere itself, a zone where particle populations mimicked interstellar conditions while the magnetic environment remained solar in origin. A kind of antechamber still inside the bubble where the ordinary markers of inside and outside had become unreliable. The argument was not fringe speculation. It was grounded in the actual measurements. The unchanged magnetic field was a documented fact. The particle transition was equally documented. Fisk's contention was that particle-based evidence alone was insufficient to confirm a crossing when the magnetic evidence contradicted it. He had a defensible point. Without direct plasma measurements, which the disabled plasma science experiment could have provided, the evidence was, by definition, incomplete. The most persuasive confirmation would have required an instrument that had been inactive for over 3 decades. Other scientists aligned with his position. The year-long debate that preceded NASA's formal confirmation in September 2013 was not procedural theater. It was a genuine scientific dispute in which credible researchers working from identical data reached opposing conclusions. Fisk maintained his position for years afterward, publishing arguments as late as 2022 questioning whether the craft had genuinely departed our star's domain. His case highlights something essential about how science actually operates at the frontier. When a spacecraft crosses a boundary that no spacecraft has ever approached before, there is no independent verification available. No one can fly out and confirm it. The only evidence comes from the instruments aboard the craft itself. And when those instruments produce conflicting readings, interpretation hinges on which instruments you weight more heavily, and which theoretical framework guides your analysis. The heliopause crossing was supposed to be definitive. Instead, it became a masterclass in scientific ambiguity. The particles pointed one way. The magnetic field pointed another. The plasma detector that could have broken the deadlock was dead. And the boundary itself turned out to be far stranger than any model had equipped researchers to anticipate. The standoff might have persisted indefinitely. It might still be unresolved, circulating through journals and conference sessions without resolution. Except that one physicist had made a prediction 20 years before the crossing had been dismissed for it, and had left behind an instrument that would ultimately settle the matter. In 1992, a physicist named Don Gurnett detected faint radio wave emissions originating from the outer reaches of the heliosphere. The signals were weak, intermittent, and straightforward to ignore. Gurnett did not ignore them. He analyzed their frequencies and used the information to estimate the distance to the heliopause as somewhere between 116 and 177 astronomical units from our star. The prediction was received with skepticism. The data was sparse. The range was broad. Other researchers classified it as speculative, the kind of projection that would only be recalled if it happened to prove accurate and would be quietly forgotten if it did not. Gurnett published his findings and redirected his attention elsewhere. The prediction sat in the literature for 2 decades, largely uncited. Then Voyager 1 crossed the heliopause at 121.6 astronomical units, precisely within Gurnett's predicted range. 20 years of being disregarded, and the data had vindicated him completely. But Gurnett's contribution extended beyond the prediction. His plasma wave instrument, still operational on Voyager 1, became the key to resolving the debate that Fisk and others had ignited. The plasma science experiment was dead. Direct plasma measurements were impossible. But the plasma wave instrument could accomplish something indirect and enormously valuable. It could detect oscillations in the surrounding medium and infer the density of the plasma around the spacecraft from the frequency of those oscillations. In the months following the crossing, the instrument registered a sharp increase in plasma oscillation frequency. The implied density jump was roughly 40-fold, from the hot, thin plasma of the solar wind to a cooler, substantially denser medium consistent with an interstellar environment. 40 times denser. The transition was abrupt and unambiguous. While the magnetometer showed no change in field direction, the plasma wave instrument captured a density shift so dramatic that explaining it as anything other than a boundary crossing was nearly impossible. This was the evidence that tipped the balance. NASA officially confirmed the heliopause crossing in September 2013, relying heavily on Gurnett's plasma wave data. The particle evidence was strong. The magnetic evidence was contradictory. The plasma wave evidence broke the tie. Don Gurnett died on January 13, 2022. He did not live to witness Pressure Front 2, the 2024 engineering emergency, or the transmitter failure that nearly silenced the mission. But his instrument continues to function, and his prediction, dismissed for 2 decades, remains one of the most precisely validated forecasts in the history of space physics. The investigation had its first confirmed crossing. The debate was resolved, at least formally. 6 years later, the second spacecraft would reach the same boundary, carrying the instrument its twin had lost. The expectation was uncomplicated. Voyager 2's functioning plasma detector would supply the direct confirmation that Voyager 1 had never been able to provide. That expectation, like so many before it in this story, was about to become complicated. On November 5, 2018, Voyager 2 crossed the heliopause at approximately 119 astronomical units from our star. 2.6 astronomical units closer than its twin had crossed 6 years earlier. The difference in distance was noteworthy, but not altogether surprising given the heliosphere's established asymmetry. What made this crossing significant was the instrument complement. Voyager 2's plasma science experiment still worked. For the first time in history, a spacecraft could directly measure the plasma transition at the heliopause rather than inferring it through secondary instruments. The data was sharp. A sudden, dramatic spike in plasma density verified the boundary. The probe had crossed from the solar wind environment into the denser interstellar plasma, and the detector had captured the transition in real time. The crossing was confirmed directly, unambiguously, with the instrument purpose-built for precisely this measurement. But several aspects refused to align neatly with the first crossing. The 2 spacecraft had crossed at different distances on opposite sides of the heliosphere years apart. Each encountered a sharp plasma transition. Each measured alterations in cosmic ray counts, and at both crossings, the magnetic field direction declined to change. Twice now. 2 independent spacecraft, 2 independent magnetometers, 2 independent crossings separated by billions of miles. Same result. The magnetic field at the heliopause does something fundamentally inconsistent with what 5 decades of theoretical work had projected. This was no longer an anomaly specific to Voyager 1. This was a confirmed property of the boundary itself. The 2 crossings together sketched a heliopause far more complex than any pre-mission model had prepared researchers to expect. Some properties changed sharply: plasma density, cosmic ray counts, the energy distribution of particles from our star. Other properties remained stubbornly continuous. The magnetic field direction, which should have been the clearest boundary marker of all, shifted smoothly or barely shifted at all. Nobody had a complete explanation. Theories circulated freely. Perhaps the magnetic fields of the heliosphere and the interstellar medium were, by cosmic coincidence, oriented similarly at both crossing locations. Perhaps the boundary layer was thick enough that the magnetic transition played out gradually over enormous distances rather than sharply at a single surface. Perhaps the interaction between the 2 fields had produced a complex, layered architecture that neither theory nor prior observation had suggested. Each hypothesis had merits. Each had difficulties. None commanded agreement. The investigation had arrived at a juncture where the confirmed data was more disorienting than the absence of data had been. Both crossings were real. Both were recorded by instruments operating at the boundary itself, and both produced a result that, by every existing theoretical framework, should have been impossible. At that boundary, the instruments also captured something that defied physical intuition entirely. At the heliopause, both Voyager spacecraft measured the temperature of the surrounding plasma. The readings returned values between 30,000 and 50,000 Kelvin. In Fahrenheit, that translates to somewhere between 54,000 and 90,000 degrees. For reference, the visible surface of our star is approximately 5,500 Kelvin. The edge of the solar system, at the point where our star's influence finally surrenders to the interstellar medium, is between 5 and 9 times hotter than the stellar surface itself. The coldest, most remote frontier imaginable turned out to be a furnace. The reason the spacecraft did not vaporize is density. Temperature in physics measures the average kinetic energy of individual particles. At the heliopause, each individual particle is hurtling at speeds corresponding to tens of thousands of degrees, but there are almost none of them. The plasma is so rarefied that the total energy it carries is negligible. Consider the analogy. A single spark from a campfire might register at 2,000 degrees Fahrenheit. If that spark lands on your hand, you flick it away. The temperature is genuine, but the particle density is so low that virtually no energy is transferred. At the heliopause, the principle scales up to cosmic proportions. Individual particles carry enormous kinetic energy. There are so few of them per cubic meter that the spacecraft drifts through entirely unaffected. But the temperature itself demands explanation. How does a region at the farthest extent of our star's reach, where the solar wind has been decelerating and cooling across billions of miles, end up hotter than the stellar surface? The solar wind near Earth's orbit runs at roughly 100,000 to 300,000 degrees Fahrenheit. By the outer heliosphere, it has cooled considerably. At the termination shock, compression reheats it somewhat, but the temperatures measured at the heliopause exceeded anything the compression-based models had anticipated. The leading explanation involves a pileup effect. As the solar wind presses against the heliopause, it compresses against the interstellar medium, converting kinetic energy into thermal energy and raising temperatures. Pickup ions, those interstellar atoms captured and accelerated by the solar wind, contribute supplementary energy that older models had never accounted for. The same pickup ions that triggered astonishment at the termination shock may also be driving the extreme temperatures measured at the heliopause. But no model yet fully reproduces the observed values. The confirmed temperature range at the boundary is an established measurement that theory continues to chase. The edge of the heliosphere was supposed to be a quiet, cooling margin where the final traces of the solar wind faded into interstellar dark. Instead, it registered temperatures that would dissolve steel if the density were even slightly higher. The investigation had now established that the boundary was asymmetric, magnetically anomalous, disputed by its own discoverers, and improbably hot. The question of its shape, the large-scale geometry of the entire heliosphere, was about to unravel. For over 55 years, every diagram of the heliosphere showed the same form. A blunt, forward-facing nose pointing in the direction of our star's motion through the galaxy, and a long tail streaming behind like a comet. The image was reproduced in every textbook, every lecture deck, every public-facing presentation about the boundary between our star's dominion and interstellar space. The comet tail was intuitive. Our star moves through the galaxy. The solar wind compresses forward, stretches behind like a windsock in a current. The physics seemed self-evident. Then the Cassini spacecraft, before its deliberate entry into Saturn's atmosphere in 2017, supplied an unexpected piece of evidence. Its instruments had been charting energetic neutral atoms, particles that form when charged solar wind particles swap electrons with neutral interstellar atoms. Those measurements spanned a wide arc of sky and generated a map of the heliosphere's boundary as observed from the inside. The shape that emerged was not a comet. It resembled something closer to a beach ball, roughly spherical, with no elongated tail. The data implied that whatever was occurring behind our star's direction of travel was not the long tapering wake that every model predicted. Simultaneously, heliophysicist Merv Ofer had been running magnetohydrodynamic simulations of the heliosphere. Her models produced no comet either. They generated something far stranger. Two lobes of solar material curling backward from our star, twisted by the stellar magnetic field into a form that from certain angles resembled a croissant. Two fat jets spiraling outward with no coherent tail at all. When she presented this at conferences, the reception was hostile. Ofer described being criticized at every conference where she introduced the croissant model. The comet tail shape was not merely a theoretical position. It was a consensus embedded so deeply that challenging it meant challenging the professional legacy of an entire generation of researchers. Publication records, reputations, and grant histories were anchored to the comet tail heliosphere. Other investigators proposed a jellyfish configuration, with trailing tendrils of magnetic field and plasma extending asymmetrically behind the structure. Cremigas captured the emotional weight of the moment. You do not accept that kind of change easily. The whole scientific community had assumed for over 55 years the heliosphere had a comet tail. As of today, confirmed by the most recent literature, no consensus exists on the shape of the heliosphere. The comet model is not discarded, but it no longer holds default status. The beach ball, the croissant, and the jellyfish are all active candidates. The shape of the bubble shielding every living thing in our solar system from galactic radiation remains genuinely unresolved. Merav Ofer had not set out to provoke a dispute. Her magneto-hydrodynamic simulations, among the most computationally sophisticated models of the heliosphere ever constructed, simply failed to reproduce the expected result. Where every previous simulation generated a comet tail, hers produced two jets of magnetized solar material curling backward from our star, twisting around one another under the influence of the rotating stellar magnetic field. The physics driving the croissant shape was specific and reproducible. Our star's magnetic field flips polarity approximately every 11 years during the solar cycle. That oscillating field imprints onto the outflowing solar wind, generating alternating sectors of positive and negative magnetic polarity. When this striped wind reaches the outer heliosphere and presses against the interstellar medium, the alternating sectors interact, reconnect, and generate a bifurcated structure rather than a smooth, trailing tail. Two lobes twisting and folding back on themselves. The results held up under repetition. Other teams running comparable simulations obtained similar structures. The underlying physics was sound. Ofer published paper after paper, each one refining the model. Each one met with institutional resistance at conferences where the comet tail had been doctrine for half a century. What made the pushback so intense was not the quality of the work. It was the implication. If the heliosphere resembles a croissant rather than a comet, then the theoretical scaffolding underpinning decades of research on how the heliosphere interacts with its galactic surroundings requires fundamental revision. Cosmic ray propagation models change. Estimates of shielding effectiveness change. Predictions about how the bubble responds to shifts in the interstellar environment change. A different shape means a different interaction with the galaxy, which means different consequences for everything sheltered inside. The Voyager data supported the complexity. The asymmetric termination shock with its 10 astronomical unit discrepancy between the two crossings was more consistent with a multi-lobed geometry than with a smooth, symmetric comet structure. The chaotic stagnation region, where the solar wind reversed and lost all coherence, was more readily explained within a geometry with complex internal dynamics than within a simple trailing tail. The unchanged magnetic field direction at the heliopause made more physical sense in a structure where the boundary was thick and layered rather than thin and sharply defined. Ofer was not vindicated overnight. The debate remains alive, but the comet tail is no longer the automatic default. That conceptual shift, representing one of the most significant changes in heliophysics this century, came about largely because one researcher kept producing results that the broader community did not want to acknowledge. While Ofer was fighting for a new geometry, a satellite orbiting Earth recorded something that didn't fit any proposed shape at all. In 2009, NASA launched the Interstellar Boundary Explorer, a compact satellite built to map the heliosphere's outer boundary from Earth orbit. It hunted energetic neutral atoms, particles generated when fast-charged particles from the heliosphere's edge exchange electrons with slower neutral atoms in the interstellar medium. Those neutral atoms, freed from deflection by magnetic fields, travel in straight lines back toward Earth, carrying information about the conditions that produced them. The Interstellar Boundary Explorer mapped these atoms across the full sky. What it found was a ribbon, a bright, narrow arc of energetic neutral atom emissions curving across the celestial sphere. The ribbon was focused, coherent, and entirely unanticipated. No existing model of the heliosphere had predicted its presence. No simulation had generated it. No theoretical account of the interaction between the solar wind and the interstellar medium had suggested that a concentrated ribbon of emissions should appear. The Interstellar Boundary Explorer team used a phrase that would be repeated for years. The ribbon bore no resemblance to anything theory had proposed. In the more than 15 years since its discovery, the ribbon has produced dozens of papers and multiple competing explanations. One leading theory holds that the ribbon marks a region where the interstellar magnetic field is perpendicular to the line of sight from Earth, producing conditions that preferentially channel secondary, energetic neutral atoms back toward the inner solar system. Another points to instabilities at the heliopause driving local enhancements in particle production. A third involves the draping of the interstellar magnetic field around the heliosphere, generating a concentrated emission zone. None of these explanations has achieved consensus. The ribbon remains among the most significant unexplained phenomena in heliophysics, a structure whose existence implies an interaction between the heliosphere and its surrounding environment that theory was entirely blind to, until an instrument happened to look in the right direction. The implications reach beyond academic interest. If the heliosphere's boundary produces concentrated emissions that no model predicted, then our understanding of how that boundary functions is fundamentally incomplete. The heliosphere is the radiation shield for the entire solar system. Grasping its boundary means grasping how thoroughly it protects us. The ribbon suggests that protection depends on mechanisms we have not yet identified. And the ribbon was not the final revelation from beyond the heliopause. In 2020, the probe that had crossed the heliopause 8 years earlier encountered something out there that nobody can account for. In 2020, Voyager 1 was traversing what was supposed to be a relatively featureless interstellar medium, more than 150 astronomical units from our star. Well past the heliopause, well beyond the stagnation region and the termination shock and every charted boundary of the heliosphere. The spacecraft was, by every definition in use, inside interstellar space. Its instruments recorded an abrupt change. Plasma density jumped by approximately 30%. Magnetic field strength increased by a similar fraction. Both measurements rose together and remained elevated for days, then weeks, then months, then years. As of the most current data available, more than 5 years after the initial detection, the elevated readings persist. Scientists designated the phenomenon Pressure Front 2. Consider how strange this is. Voyager 1 is moving through a region textbooks describe as an empty void between stars. Thin, uniform, slowly evolving over light-year scales, encountering a sharp, persistent structure along the trajectory of a single spacecraft was not anticipated. There should be nothing out there capable of sustaining a 30% jump in density across half a decade. Nobody understands what Pressure Front 2 is. The hypotheses extend from a compression wave launched by a distant stellar event, perhaps a supernova shock that has been propagating through the interstellar medium over thousands of years, to the boundary of a previously unknown interstellar structure, a wall of denser material that the heliosphere is either approaching or already pressing into. Some researchers have suggested it may be linked to the heliosphere's own wake, a disturbance generated by our star's passage through the medium that Voyager is now encountering from the other side. Each hypothesis carries problems. A supernova shock should lose coherence across the distances involved. A stationary wall of denser material should have registered in other observational channels. A heliospheric wake should exhibit predictable properties that the data does not fully reproduce. What Pressure Front 2 confirms, through real-time measurements from instruments operating 15 billion miles from Earth, is that interstellar space contains organized, persistent, measurable structures that appear on no existing map because no instrument had ever been positioned out there to record them. We have exactly one data point on each structure, from exactly one trajectory through the interstellar medium, observed by exactly one spacecraft. The investigation was accumulating mysteries more rapidly than it was resolving them, and the man who had held the entire effort together for half a century was running out of time. Ed Stone became Voyager's project scientist in 1972, 5 years before the spacecraft would launch. He was present for the design reviews, the instrument selections, the funding battles, the Jupiter encounter, the Saturn decision, the Uranus surprise, the Neptune triumph, and every boundary crossing that redefined the outer edge of the solar system. 50 years. He held that position longer than most people sustain any single role over an entire career. Under his direction, a mission designed to last 4 years across 2 planets was transformed into the longest-running planetary exploration in human history. The budget fights alone would have broken most scientists. The grand tour's cancellation, the piecemeal extensions, the unending need to justify the mission's continued existence to Congress, to NASA administrators, to a rotating cast of decision-makers who did not share Stone's conviction that the outer heliosphere was worth the investment. He navigated it all, not through political skill or force of personality, but through an absolute fidelity to the data. When the termination shock defied predictions, Stone organized the analysis. When the heliopause crossing ignited a year-long dispute, Stone managed the competing factions. When Leonard Fisk argued the craft had never departed, Stone ensured the dissenting position received fair consideration alongside the majority view. Linda Spilker, who succeeded Stone as project scientist in 2022, described the team's culture in a way that captures how deeply personal the mission had become. "We had our kids around the same time," she recalled. "We would take vacations together. This was not a rotating pool of anonymous engineers. It was a family aging in parallel with a spacecraft, bound together by a shared commitment to a machine that remained perpetually one budget vote away from silence." Jaime Rankin became deputy project scientist at 34. She was born after Voyager launched. The generational transition was real and carried urgency. The institutional knowledge carried by Stone, by Gurnett, by the engineers who had designed the instruments in the early 1970s existed nowhere else. When Stone retired, and when Gurnett died, that knowledge contracted. Each departure removed something that could not be recovered. Suzanne Dodd managed the project with a staff of 15 to 20 people. 15 to 20 for the most distant human-built objects in existence. The team was smaller than the staff of a mid-sized restaurant. Every member carried responsibilities that would occupy multiple positions at a larger operation. Ed Stone died on June 9, 2024, at the age of 88. At the time of his death, every central question of the mission remained open. The shape of the heliosphere, the nature of the heliopause, the origin of the anomalous cosmic rays, the meaning of Pressure Front 2, the magnetic field anomaly at the boundary. 50 years of investigation, and the fundamental question of where the solar system ends was further from resolution than it had been when he began. A new paper was about to arrive that would make that question still harder, and would challenge the very concept of the heliopause crossing that had defined Stone's legacy. In 2024, a research team led by Turner published work that reframed the heliopause in a way that unsettled the core narrative of the entire Voyager mission. The heliopause, they argued, drawing on analysis of both Voyager datasets and complementary measurements from the Interstellar Boundary Explorer, was not a thin wall. It was a thick boundary layer, a transitional zone of uncertain width where the solar and interstellar environments blended gradually, rather than meeting at a defined interface. The implications rippled through every conclusion drawn from the two crossings. If the heliopause is thick rather than thin, the unchanged magnetic field direction abruptly makes sense. A gradual transition would allow our star's magnetic field to persist deep within the boundary layer, evolving slowly rather than flipping at a single surface. The stagnation region, that chaotic buffer zone where the solar wind dropped to zero and reversed, could be reread as the inner edge of a vast transitional layer, rather than a separate phenomenon encountered on the approach. The 40-fold plasma density jump detected by Gurnet's instrument might mark one threshold within the layer rather than the layer's outer edge. But the most consequential implication was for the crossing itself. If the heliopause is a thick boundary layer, what does crossing it actually mean? Is Voyager 1 in interstellar space, or is it still somewhere inside the boundary, suspended in the transitional haze between our star's domain and the genuine interstellar medium? Bill Kurth, who had worked alongside Gurnet for decades, stated the situation plainly. Voyager will not reach the pristine interstellar medium until a further boundary is crossed, he said, and that boundary is likely 100, or more astronomical units beyond Voyager 1's current position. Nathan Schwadron, an independent researcher studying the heliosphere's outer architecture, agreed. Pristine interstellar space, the space genuinely free of any trace of our star's influence, may be 100 or more astronomical units still ahead. Run the numbers. Voyager 1 is currently at approximately 165 astronomical units. If pristine interstellar space begins at 265 astronomical units or further out, the spacecraft has covered barely 60% of the distance to the actual frontier. The celebration of 2012, the press conference, the headlines, the declaration of the first human-built object in interstellar space may have marked an exit that has not yet finished unfolding. The Turner paper did not dismiss the crossing as meaningless. The plasma transition was real. The cosmic ray shift was real. Something significant occurred at 121.6 astronomical units. But the binary framing of inside versus outside collapsed under the weight of the accumulated data. The heliosphere does not end at a wall. It fades over a distance that may extend for hundreds of astronomical units. And Voyager, our only instrument within that fade, is losing power. Each Voyager spacecraft launched carrying 470 watts of electrical output, generated by 3 radioisotope thermoelectric generators. These devices convert the heat released by decaying plutonium-238 into electricity. The decay is inexorable. Plutonium does not negotiate with budget pressures or scientific disputes. It decays at a fixed rate, and with it the electrical output falls by approximately 4 watts every year. In 2025, each spacecraft operates on fewer than 300 watts, less than a standard household appliance, less than the output needed to run 2 incandescent bulbs. Every watt must be allocated deliberately, and those allocation decisions have become agonizing. The team, led by project manager Suzanne Dodd, with a staff of 15 to 20, has been making choices with no good options. Instruments have been powered down one by one over the years. Each shutdown permanently seals off a view of a region of space that no other instrument can observe. The heaters maintaining fuel line temperatures have been scaled back. Redundant systems have been deactivated. Every function that is not strictly essential has been stripped away, leaving only what is necessary to gather data and send it home. In 2025, only 3 instruments remain active on each spacecraft. 3 out of an original complement of 11. On February 25, 2025, the cosmic ray subsystem aboard Voyager 1 was shut down to preserve power. This was one of the instruments that had detected the heliopause crossing in the first place. The very tool that contributed to confirming the most consequential moment in the mission's history was sacrificed so that other instruments could remain operational for a few additional years. Every instrument shutdown is permanent. There is no reversal. The power will never recover. The plutonium will keep decaying. The output will keep falling. And sometime in the early 2030s, there will be insufficient power to operate any scientific instruments whatsoever. Voyager will continue to move through space, carrying its golden record and its silenced instruments, but it will stop returning data. The investigation has a deadline, and it is arriving faster than any successor mission could reach position in time to matter. The Oort cloud, the spherical shell of icy bodies defining the gravitational boundary of the solar system, begins at roughly 2,000 astronomical units. At Voyager's current speed of approximately 38,000 miles per hour, reaching the Oort cloud will require roughly 300 years. The spacecraft will have gone dark long before it gets there. But before the power runs out, the spacecraft itself very nearly went permanently silent for an entirely different reason. In late 2023, Voyager 1 stopped making sense. The data stream, already a whisper at 160 bits per second from more than 15 billion miles away, deteriorated into gibberish. The flight data subsystem, which packages science and engineering data for transmission to Earth, began generating garbled, repetitive patterns containing no usable information. For anyone who has experienced a corrupted hard drive or a misbehaving computer, the situation is familiar at a household scale. Now place that computer 15 billion miles away. It was assembled in the early 1970s. It carries 3 million times less memory than a modern phone. It cannot be physically reached. Every command takes over 23 hours to arrive, and every response takes over 23 hours to return. A single exchange takes nearly 2 full days. The fault was eventually traced to a damaged memory chip within the flight data subsystem. One chip, among the small number still functioning in the spacecraft's ancient computing architecture, had failed. The data that should have been organized, formatted, and transmitted in coherent packets was instead being scrambled, looped, or dropped entirely. There was no mechanism to replace the chip, no spare components, no repair mission, no automated system capable of swapping hardware. The engineers at the Jet Propulsion Laboratory had to resolve the problem using only commands transmitted across 15 billion miles of space, and whatever functioning hardware remained aboard the spacecraft. For 5 months, the team worked the problem. The solution they devised was remarkable. They extracted the code that had been stored on the damaged chip, divided it into smaller pieces, and redistributed those pieces across available memory locations elsewhere in the spacecraft's computers. This required composing new software, validating it as carefully as possible without access to any identical hardware to test against. The last ground-based test units had been decommissioned years earlier. The team uploaded the revised code across a signal link with a 23-hour one-way delay and waited to learn whether a 47-year-old computer in interstellar space would run it correctly. On April 20, 2024, science data was restored. The spacecraft was operational again. From 15 billion miles away, engineers had performed corrective surgery on a computer older than most of the people working on it, using a signal weaker than a billionth of a watt, across a communication lag of nearly 2 days. And they had succeeded. They had barely recovered from that before. 6 months later, the primary transmitter failed. The heliosphere is not a subject of academic interest only. It is the radiation barrier protecting every organism that has ever existed in this solar system. Galactic cosmic rays, high-energy particles generated by supernova explosions, neutron star mergers, and other catastrophic events distributed across the Milky Way saturate interstellar space. They travel near the speed of light. They carry sufficient energy to damage DNA, compromise electronics, and alter the chemistry of planetary atmospheres. Without the heliosphere deflecting and absorbing the majority of these particles, the radiation environment at Earth's surface would be dramatically more hostile. The measurements at the heliopause confirmed this directly. When Voyager crossed the boundary, galactic cosmic ray counts tripled. Inside the heliosphere, the bubble intercepts and deflects the bulk of incoming galactic radiation. Outside, the full intensity of the galactic particle environment is unattenuated. The heliosphere reduces cosmic ray exposure on Earth by approximately 2/3. Every organism in the history of this planet has lived under the protection of that structure. But the implications reach beyond the present. Our star is currently passing through a region of relatively low-density interstellar gas called the local interstellar cloud. The heliosphere's scale and geometry reflect in part the density of the material pressing against it from outside. A denser external medium compresses the bubble, contracting it and diminishing its shielding effectiveness. A less dense medium allows it to expand. Within approximately 2,000 years, our star is projected to enter a region called the G-cloud, a denser patch of interstellar material. A denser external environment would compress the heliosphere substantially, potentially shrinking the protective bubble and exposing the inner solar system to elevated galactic cosmic radiation. How much higher depends on the heliosphere's shape, its thickness, and the dynamics of compression. Precisely the questions that Voyager's data has demonstrated we cannot yet answer. The shape debate matters. The thickness of the heliopause matters. The stagnation region, the magnetic field anomaly, the unknown architecture of the interstellar medium ahead. All of it feeds into a question carrying direct consequences for life on Earth. How durable is this shield? And what happens to it when the external pressure increases? The answers depend on instruments that are failing in real time aboard a spacecraft the government may not fund long enough to supply those answers. Voyager is not managed by a large organization. The mission overseeing the most distant human-built objects in existence operates with a team smaller than the staff of most neighborhood restaurants. Suzanne Dodd manages the project. Linda Spilker, who assumed the role of project scientist after Ed Stone's 50-year tenure, provides scientific leadership. Jaime Rankin, the deputy project scientist, was 34 when she was appointed, born years after the spacecraft launched. The full staff numbers between 15 and 20 people. These are not interchangeable roles. The institutional knowledge required to operate Voyager, to navigate its aged computer architecture, to diagnose instruments designed half a century ago, to interpret data from a spacecraft whose documentation exists partly in the memories of people who have since retired or died, cannot be conveyed through any training document. It lives in the individuals who have invested years or decades in the mission. Spilker's description of the team conveys something that organizational charts cannot. "We had our kids around the same time," she said. "We would take vacations together. This is a group bound by shared decades, shared milestones, and shared apprehension over budget decisions and instrument failures, and the slow, unrelenting decline of a power source that cannot be replenished." One engineer was described as the last person to have physical contact with both Voyager spacecraft before launch. That description carries weight, the tangible connection between human hands and the hardware that now travels 15 billion miles away. The chain of that physical contact runs from the engineers of the 1970s to the probe drifting in whatever lies beyond the heliopause. When Ed Stone died in 2024, institutional memory contracted. When Don Gurnett died in 2022, it contracted again. Each departure removes knowledge that exists nowhere else. Information that was never documented because nobody imagined the mission would still be operating 4 decades after launch. In July 2025, the threat became systemic rather than individual. More than 280 NASA employees signed a public statement protesting proposed budget cuts that would reduce NASA's science funding by 47%. Voyager, already running on minimal staff and minimal power, was listed among the endangered missions. The Deep Space Network, the constellation of large radio dishes in California, Spain, and Australia that receives Voyager's signal, requires sustained funding to operate. Reduced budgets translate into fewer listening hours. For Voyager, whose signal already sits at the edge of detectability, any reduction in antenna time could mean losing data that can never be recovered. Silence on the ground is indistinguishable from death in space. Yet, even as the mission faced pressure from both physics and politics, the spacecraft produced one more engineering miracle, one involving hardware that had been dormant and unexamined for 4 decades. In 1977, Anne Druyan sat in a laboratory and had her brain activity recorded by an electroencephalograph. The electrodes traced the electrical output of her mind for roughly 1 hour. The resulting data was condensed into approximately 1 minute of audio and inscribed into both golden records mounted on the Voyager spacecraft. Days before the recording session, Druyan had fallen in love with Carl Sagan during a late-night telephone conversation about the record project. They had told no one. The relationship was new, private, and electric. As the electrodes mapped her neural activity, Druyan later said she was thinking about the full span of human history, about love in the abstract, and about what it meant to be falling for a specific person in a specific irreproducible moment. Knowing those electrical signals would be pressed into a gold-plated copper disc and sent beyond the reach of our star, Sagan later ended his marriage to Linda Saltzman Sagan, who had also contributed to the Voyager project. The personal cost was real and unambiguous. A professional collaboration fractured by a love affair that had begun during a phone call about what sounds to transmit toward the stars. There is nothing clean about it. There is nothing symbolic or carefully arranged. It is simply a thing that happened, entangled with the production of an artifact now traveling through whatever space Voyager currently inhabits. Those brain waves are at this moment approximately 15.44 billion miles from the laboratory where they were recorded. They are moving at 38,000 miles per hour through the dense boundary layer of the heliopause medium, or perhaps through something in between that has not yet been given a name. A record of falling in love, encoded in the universal language of electrical activity, carried by a machine whose own survival has become an improbable testament to what a small group of people can sustain. The golden record was conceived as a transmission from our species to any intelligence that might someday find it. In practice, the probability of another mind encountering either Voyager spacecraft is so infinitesimally small that the record operates differently from its original intent. It is a message from us to ourselves, a declaration of what we considered worth preserving at a particular moment in our existence: music, images, greetings, natural sounds, and the brain waves of a woman in the first hours of falling in love. Everything about Voyager carries this quality. The budget disputes, the naming confusion, the dead instrument, the arguments about whether the craft actually left, the team that raised their children alongside a spacecraft, the love affair that consumed a marriage and deposited its neural trace somewhere past the heliopause. And in October 2024, the most human chapter of All arrived. The spacecraft nearly died, and something assembled 4 decades earlier, unused and almost forgotten, woke up to save it. In October 2024, Voyager 1's primary X-band transmitter failed. The X-band system had been the principal communication link between the spacecraft and Earth since launch. It operated at a higher frequency and transmission rate than the backup, generating the signal the Deep Space Network had tracked across 47 years. When it went dark, the connection between Earth and its most remote explorer was severed for a craft 15 billion miles out. Losing the primary transmitter should be a terminal event. There is no repair call. There is no replacement component. There is no fallback when your hardware is farther from any human being than any object has ever been. But Voyager 1 carried a backup, an S-band transmitter installed alongside the primary before launch. It had been designed as a failsafe for exactly this eventuality. There was one detail that made its continued viability improbable. The S-band transmitter had last transmitted in 1981. 43 years of dormancy. 43 years adrift in the vacuum of space, absorbing cosmic radiation, cycling through temperature extremes, accumulating the degradation that time presses onto all electronic components. Nobody knew whether it would respond. The spacecraft's onboard fault protection software detected the X-band failure. Without any instruction from Earth, without any human involvement, the software executed a pre-programmed sequence. Switch to the backup transmitter. The command passed through circuits that had been conducting current for 47 years, reached a transmitter that had been silent for 43 of those years, and asked it to activate. It activated. A transmitter manufactured in the early 1970s, last used when the first space shuttle had not yet flown, powered on, and began sending data back to Earth. The signal was weaker. S-band operates at a lower frequency and supports a reduced data rate compared to X-band. But the signal was there. The Deep Space Network acquired it. Engineers on the ground, most of whom had not been born when the backup was last used, confirmed the signal and began extracting data. The mission was alive. Hardware engineered by people who had long since retired or died, produced by companies that may no longer exist, built to standards that predate the personal computer, had preserved the most distant human-built object from permanent silence. No simulation had prepared anyone for this scenario. No ground-based prototype existed to test whether the backup would function after 4 decades of disuse. Engineering education instills the value of redundancy as a design principle. What it cannot transmit is the particular alchemy of a backup system that revives after 43 years for reasons that any precise engineering model struggles to predict. Some combination of manufacturing quality, conservative design margins, and fortune maintained. Those circuits across 4 decades of radiation exposure and vacuum. The spacecraft now communicates on that backup system. Every piece of data from interstellar space, every magnetic field reading, every measurement of plasma density travels home through a transmitter that was last active during the height of the Cold War. In July 2025, 280 NASA employees added their names to a public declaration. The document opposed proposed budget cuts that would reduce NASA's science funding by 47%. Voyager appeared among the listed missions at risk. The math of the threat was direct. Voyager requires the Deep Space Network to receive its signal. 3 facilities around the world, in California, Spain, and Australia, maintain massive antenna systems capable of detecting the spacecraft's vanishingly faint transmissions. Those facilities support multiple missions. Reduced funding produces reduced operating hours. Reduced hours mean some missions lose antenna time. For a spacecraft, transmitting at the effective power of 10 to the negative 16 watts, every lost hour of antenna coverage represents irretrievable data from a region of space accessible by no other means. All 280 signatories were advancing an argument that extended beyond any single project. Both Voyager spacecraft are beyond replacement. There is no alternative mission in preparation. No spacecraft currently under construction will reach interstellar space within any reasonable human timeline. The distance the probes have covered required nearly 50 years of continuous flight. Any replacement launched today using available propulsion technology would take decades just to approach the heliosphere's outer boundaries, and would arrive long after the original Voyagers had transmitted their last signal. Every measurement Voyager is currently collecting about the thick transitional boundary layer of the heliopause, about pressure front 2, about the magnetic field anomaly, about the structures encountered within interstellar space cannot be gathered through any other means. If funding reductions silence the ground stations before the power source fails, the data will be permanently lost. The spacecraft will keep transmitting faithfully on its 43-year-old backup transmitter, and no one will be receiving. None of this is abstract. The cuts were formally proposed. The declaration was formally signed. The political process determining Voyager's survival continues. The same category of congressional budget decision that nearly terminated the mission before it launched 50 years ago, when the Grand Tour was judged too expensive, now threatens to end it before the investigation reaches any conclusion. And the investigation is nowhere near a conclusion. The shape of the heliosphere is unresolved. The thickness of the heliopause is unresolved. The source of the anomalous cosmic rays is unresolved. Pressure front 2 is unexplained. The magnetic field anomaly at the boundary remains without a satisfying account. The question that launched this entire undertaking, where the solar system ends, remains as genuinely open as it has ever been. What waits ahead for a spacecraft that may or may not survive long enough to keep asking reveals just how incompletely the frontier has been explored. Voyager 1 is currently approximately 165 astronomical units from our star, traveling at roughly 38,000 miles per hour. That velocity sounds substantial. Against interstellar distances, it is barely adrift. The Oort cloud, the vast spherical repository of icy bodies that defines the gravitational perimeter of the solar system, begins at roughly 2,000 astronomical units. At current speed, Voyager 1 will reach the Oort cloud's inner boundary in approximately 300 years. Traversing it will require roughly 30,000 years. The Oort cloud is so immense that even at 38,000 miles per hour, passing through it takes longer than all of recorded human history. Around the year 40,272, Voyager 1 will pass within roughly 1.6 light-years of a faint red dwarf star designated Gliese 445 in the constellation Camelopardalis. By then, the spacecraft will have been silent for tens of thousands of years. A motionless artifact carrying a gold-plated copper record and the dormant charge of instruments that exhausted their plutonium in the 2030s, drifting through the stellar neighborhood of another sun. Consider what those numbers mean for the original question. If the boundary of the solar system is defined gravitationally, by the extent of our star's influence over the comets and icy objects in the Oort cloud, then Voyager has covered less than 1/10 of the distance to the edge. 165 astronomical units of 2,000. A fragment. The gravitational solar system is far larger than the heliosphere, and the spacecraft is nowhere near its outer margin. If the boundary is defined by the heliopause, the plasma transition both probes detected, then Voyager crossed in 2012. But Turner's thick boundary layer suggests the craft may still be threading through a transitional zone, not yet immersed in pristine interstellar space. Bill Kurth's estimate places the true interstellar medium 100 or more astronomical units further on. At that definition, the answer to whether Voyager has left is tentative and conditional. If the boundary is defined by the pristine interstellar medium, free of any influence from our star, then the estimates from multiple researchers suggest the craft has potentially hundreds of astronomical units still to cover. The answer, by that definition, is clearly no. The question of where the solar system ends does not resolve to a single answer. It produces multiple answers, each tied to a different physical definition, and Voyager's data has made every definition more problematic and less satisfying than it was before any measurements existed. In 2012, the world was informed that Voyager 1 had departed the solar system. The data frames a more complex story, not a tidier one, not a more conclusive one. A stranger, more unsettled one that remains unfinished. The termination shock was not symmetric. The heliosphere is lopsided, pressed inward by the interstellar medium on one side. The anomalous cosmic rays were not accelerated where 5 decades of theory held they would be. The pickup ions carried energy that exposed fundamental gaps in the energy budget of the termination shock. The plasma detector that could have resolved the heliopause dispute was dead, disabled at Saturn 32 years before the boundary was reached. The stagnation region, a 900-million-mile zone of chaotic, reversed solar wind, materialized without warning in a region no model had designated for it. The heliopause crossing, when it came, produced the anticipated particle signatures and the entirely unanticipated magnetic result. The field direction held steady. 2 crossings, 2 spacecraft, identical anomaly. Don Gurnett projected the heliopause distance in 1992 and was laughed at. He was correct. His instrument resolved the debate. He died before the next generation of mysteries surfaced. Merav Ofer modeled the heliosphere as a croissant and was challenged at every venue she presented it. Her simulations are now among the lead contenders for the true geometry. No agreement has been reached. Leonard Fisk maintained the craft had never left. The thick boundary layer described by Turner suggests he may have been nearer the truth than anyone was prepared to concede. The interstellar boundary explorer returned a ribbon across the sky that no theory had forecast. Pressure Front 2, a persistent wall of elevated density and magnetic pressure inside the interstellar medium, remains without explanation more than 5 years after detection. The heliopause is hotter than the surface of our star. The shape of the heliosphere is unknown. Interstellar space contains structures that nobody mapped, because nobody had an instrument positioned to map them. Voyager 1 communicates through a backup transmitter last used in 1981. Its primary transmitter is gone. Its cosmic ray detector was deactivated in February 2025. 3 instruments remain. Power contracts by 4 watts every year, and the plutonium does not yield to argument. The team is 15 to 20 people. The budget faces a 47% reduction. 280 NASA employees have formally objected. The question that initiated this investigation, where does the solar system end, is further from resolution today than it was when Voyager lifted off in 1977. Every boundary the probe crossed proved more intricate than predicted. Every model it tested failed in ways that multiplied the questions rather than reducing them. The edge of the solar system may be a line or a fog or a transitional zone hundreds of astronomical units deep. It may be delineated by plasma or gravity or magnetic architecture or by a pristine interstellar medium that no instrument has yet penetrated. The only machine capable of advancing the investigation is 15.44 billion miles out, drawing power from decaying plutonium, operating on 3 instruments and a 43-year-old backup transmitter, carrying a golden record that holds the neural signature of a woman in the earliest moments of falling in love. The investigation remains open. The machine is dying. There is nothing ready to replace it. And somewhere in the long silence ahead, past whatever pressure front 2 turns out to be, past the thick fog of the transitional heliopause, past everything we have named and everything we haven't, the true interstellar medium waits, and Voyager drifts toward it with no awareness of what it carries or what it has already changed about our understanding of where we live in this galaxy.